Okay, it looks like we're going to have a small group today. Welcome everybody to our virtual cafe. And let's see if anybody else will chime in. This is Cafe. I'm Frank Gomez, Executive Director of STEMnet, Monica Lacon, Operations Analyst at STEMnet. Much thanks to her for sticks and publicizing the event. The goal of the cafe is to foster research across the CSU that may end up being a submission of a proposal later on, but at least maybe a collaboration going forward. Please feel free to contact any presenter in the chat box when they're not presenting. At the end of the 3 presentations, we'll all come together and we'll have a Q&A for about 20-25 minutes or something like that. So we have 3 great speakers today presenting a snapshot of their work. Our first speaker is Dr. Laurie Huning from the Department of Civil Engineering at the Beach, Cal State Long Beach. Laurie, the floor is yours.
All right, thank you very much. Let me go ahead and share my screen. All right, you should be able to see my slides, right?
Yes, we see your slides.
Okay, perfect. Hi, everyone. Before I get started, I just wanted to quickly say thanks again to the STEM folks for organizing these meetings and inviting me to give this presentation. As Frank mentioned, my name is Laurie Huning. I'm an assistant professor at CSU Long Beach in the Department of Civil Engineering. So broadly speaking, my research is in the areas of hydrology, extreme events, and climatology. One of the overarching aims of my research is to address local to global water challenges and understand how climate change and variability influence our current and future water resources. And what makes hydrologic research, I think, incredibly interesting and important is how interconnected the water cycle is. So precipitation, evaporation, runoff, and our water resources. And these are interconnected with various industries such as hydropower, agriculture, and in many cases, very tightly coupled to socioeconomics around the world. So my research focuses on trying to better characterize these key hydrologic variables and how they vary because they can have far-reaching impacts. So given the rise in global temperatures over recent years and the projected future warming of our climate, much of the world is expected to see an increase in a variety of different types of extremes. So heat waves, droughts, floods, wildfires, and extreme precipitation, just to name a few. As you can see here in this graph, the United States has been experiencing an increasing number of billion-dollar weather events and extreme events. So one of the goals of my research is to better understand the drivers of extreme events, as well as their impacts as they propagate both in space and time. And this can be challenging because our existing in situ observational networks, such as those shown here, well, they often have large gaps in their spatial coverage, especially in areas of complex terrain where we know that precipitation and the snowpack can have very high variability. So, for instance, let's say we go to the field, like you can see here in the photograph on the left, which is from April 2015. So we go to the field to take a snow measurement. Well, there's no snow in sight. So how do we estimate how much snow is located elsewhere in a mountain range if where you're currently sampling, there's none to be seen? Well, we also need to think about not just our in situ network, but what about how well our models are working? How well do they estimate the amount of water stored in the snowpack or the snow water equivalent? So let's take a quick look at some model estimates. So if you look at the panel on the upper left, what we're seeing here is a multi-data set model mean. So you can think of this as multi-data set, multi-model estimation of snow water equivalent. Again, how much water is stored in the snowpack. So if you take this figure, divide by the spread among those same models, what you'll get is that lower left-hand panel. And what you'll notice now is that across the Northern Hemisphere, most of the Northern Hemisphere is now shaded blue, which indicates that there's a high uncertainty, high variability among those model estimates. Okay, so this gives us kind of a larger scale perspective of how well our models are doing. But what if we zoom into a mountain range? And this is actually a question that we asked in a recent publication, where we just simply said, okay, let's look at the Sierra Nevada mountain range and compare over 10 different models and reanalysis. Well, what we found was we get about 10 different model estimates of the snow water equivalent. But what's even more striking is the fact that it's not just that we get 10 different estimates, but we essentially have a range, a whole spectrum of estimates going from essentially no snowpack to a fully developed snowpack. So with this in mind, we have deficits or deficiencies, spatial gaps in our in situ network, and also a lot of uncertainty and variability with our models. So we can utilize remote sensing along with those in situ observations and modeling to better understand how much water, say, is stored in the snowpack, where is it stored, and how to better manage our water resources, especially in regions like California or the Western US, which are highly dependent on snowmelt for a large fraction of their water. And this is really where my research comes in. So in fact, we can leverage complementary information from a variety of different data streams, including in situ observations, as I've already mentioned, and remote sensing-based estimates of hydrologic variables to create data sets that would otherwise not be possible. So for instance, what I'm showing here, we used a spatially sparse snow cores field observations that have a long temporal record of SWE depth, so again, snow water equivalent, along with a spatially distributed remote sensing based information, which has a shorter temporal record because it's restricted to the satellite era. But those actually give us estimates of the SWE volume. And we combined and merged these two data sets together to develop nearly 80-year-long data set to quantify the amount of water stored in Sierra Nevada snowpack. And this data set is nearly twice as long as other existing data-driven SWE records. And we use this data to compute SWE return periods, which is important because the amount of water stored in a snowpack can be closely related to both flood and drought potential in a region. So my research spans from the global to regional to local scales, which is important for quantifying and characterizing different processes and understanding, what the dominant processes are across various spatial and temporal scales. When are they most important? How do they vary? And perhaps maybe most importantly, how do they interact with one another? So far, I've shown an example of my work across a mountain range. There we go. But I've also led, global studies. In fact, what I'm showing here is results from the first ever global snow drought assessment. And when I'm mentioning snow drought, what I'm referring to is a deficit in the amount of water stored in the snowpack, or in other words, SWE. So we applied our snow drought framework to identify how the duration and intensity and severity of snow droughts are changing across the globe. And in doing so, we identified 3 regions that emerge as snow drought hotspots, having longer and more intense snow droughts over the last 20 years compared to previous 20 years. And 3 regions emerged: the Western US, Europe, and Eastern Russia, all having longer duration and more intense snow droughts that recently occurred. So using these types of frameworks, we can better assess how much snow how much of various variables or different quantities, hydrologic quantities, are present in regions, say, where there's very few or possibly no in situ measurements of that variable of interest. And so what I'm very interested in doing is, taking these frameworks related to various hydrologic quantities and tying them into better understanding impacts. And so we've begun to start to work in that realm to understand the impacts of our changing water supply on, say, agriculture, global trade, because again, we have local to large scale couplings and interactions that really impact the socioeconomics around the world. So it looks like I'm running out of time here, but I just really want to quickly mention that we're looking into the effects of warming both in historical and future time periods to again understand what are these impacts from a local scale and how do they propagate from a local region to downstream areas that both use water for drinking water, agriculture, or other various applications. So in closing, I just highlighted a few studies that I've worked on related to the snowpack, but my research also involves other areas of hydrologic cycle. So if you're interested in discussing more about my research or have any questions, please feel free to reach out. Thank you for your time.
Thank you, Laurie, for a very interesting talk, and I'm sure there'll be questions come the end of our presentations.
Sounds good.
Next speaker is Laurie Cappiello from Sac State. Lauren.
All right, let me share my screen. Okay, got all this Zoom stuff moved around. All right. Good morning. Again, I'm Laurie Cappiello. Be talking about some statistics stuff. Well, make sure I can click through that. So a little about me. Again, I'm here at Sacramento State. I'm in the math and statistics department here. I do teach both math and statistics classes, but I consider myself a statistician. My PhD is in applied statistics. And I've been here since fall 2020. I grew up between Arizona and Oregon. I've been here in California since 2013. I did my PhD at Riverside, and I graduated from there in 2020. A little more about me. That one kind of fun fact is I have a lot of animals. So these are my cats and these are my dogs. Okay, so let me talk about my research a bit. So the kind of I guess heavier duty stats research that I've worked on is in causal inference, applied machine learning, and really applied machine learning means non-parametric statistics. So this was a big project that I did, both my dissertation and some ongoing research works on this kind of thing. So the big kind of question here is that when we run studies in general, random or experiments, and in particular, and this is in a medical setting, we have some population of interest that we would like to sample from. But because of all kinds of different things, in particular in a medical context, we have some kind of eligibility criteria for the study. Always when we want to get a random sample with human subjects, we have issues of people have to consent to be in the study, and often they have to consent to be randomly assigned to a treatment. So questions of who's willing to consent to a study and who is eligible mean that the actual population that we get our random sample from is not our target population, and it is in fact a distinct population. So we take a random sample, that's all good, but it does come from this distinct population, which is a subset of our population of interest. And then that random sample, we split people into different, treatment arms, treatment and control. So the kind of broad, let me just glance here. The kind of broad question that we work on with this, and that I added a lot of like non-parametric approaches to, is that we want to be able to estimate either those treatment outcomes and the control outcomes, so the actual measurable outcome in each group, or the difference between treatment and control. When we estimate those based on our sample, what we're getting is an estimate of those values from the study population and not from the target population. So I've done a lot of work in this problem and I'm saying, okay, we can estimate that easily for the study population. What are some ways to then do those same estimates, but for the target population? So it turns out that if we can get data from that target population, which in a medical context, we can also often get from like medical or insurance records, Medicare type records, we can actually learn quite a lot about that treatment outcome, control outcome, and the difference between those two in the target population, even though we don't have data that's representative of the target population, which is pretty cool. Okay. Since I've been here at Sac State, most of the work that I've been doing is applied statistics. That's what I really love to do. I love to work with other researchers and learn about other people's research. So some recent stuff that I did all the data analysis for this American Council of Physical Therapy survey. And I've been working with a student on non-parametric analysis. She worked a lot last year on differences and variances for someone in biology here at Sac State. We're continuing to look and work with that same lab this year, looking at data analysis. So I enjoy the data analysis piece as well as the kind of applied statistics piece. Currently, some stuff I'm working on. I have a consulting contract with the state controller's office, so I do a lot of like audit sampling work for them. And I do training for them as well. I'm on a project looking at equity and academic career pathways. And that project uses data from the National Center for Science and Engineering Statistics. We're trying to work on a paper looking at essentially pathways to the professoriate, like who becomes a professor, and examining maybe some barriers to getting to academia. And then I'm also working with a student. This relates to this non-parametric analysis of differences and variances. Last year, we noticed that sometimes so we're using non-parametric tests because the data are heavily skewed. And we noticed that with really, really extreme skew, even the non-parametric tests were performing poorly. Outcomes were unexpected. And so we are currently working on a simulation study to compare different techniques for those type of analyses. We're looking at a few different non-parametric tests as well as, or semi-parametric tests, as well as some fully non-parametric tests in the form of like bootstrap testing. That's a current thing we're working on. In terms of collaboration stuff I'd like to do, like I said, I really enjoy the data analysis piece. I really like to work with other people's data. I really like to just learn about what other people are working on. And I'm also happy to do sort of brief for shorter consulting type work and just sort of talk through a problem that someone might have, whether or not you actually need someone to analyze all the data. I'm always happy to just sit down and kind of brainstorm approaches to your data. And then, of course, any sort of data analysis that maybe or study design, where maybe there's a level of complexity that some novel approaches are required to kind of get through your research problem. So yeah, I think that was a little short, but that's what I have. And I'd be happy to talk about any of your statistics needs.
Great, thank you, Lauren. And I'm sure there'll be some questions in a few minutes. Our last speaker is Theresa Migler from Cal Poly SLO from the Computer Science Department. Theresa.
Hello. Can everybody hear me? Yes. Good. Okay, great. Well, thank you so much for inviting me. I'm excited to talk a little bit about graph theory. So let me share my screen. Okay, and some of the neat projects that I'm working on. Whoops. Okay. So again, my name is Theresa Migler. My pronouns are she, her, and hers, and I'm an assistant professor in the Computer Science and Software Engineering Department at Cal Poly in San Luis Obispo. And so let me get started. So the title of the next 10 minutes is Graphs as a Guide to Research, Collaboration, and something we're all very interested in these days, which is cough prevention. So I'm a hidden mathematician in the computer science department. So what you'll see is very mathematical in nature, but I definitely, well, let's just go. Okay, so what is a graph? That's our first question. Well, most of you probably know that a graph is a set of vertices and a set of relationships on those vertices. And so we call these relationships, the vertices that have relationships between them, we say that they're connected by edges. So in this simple graph right here, our vertices are A, B, C, D, and E. And you could say like A and C have some sort of relationship, and so they're connected by an edge. Now I'm going to go through and give you some graph metrics of interest, along with hopefully 3, maybe 4 of the projects that I'm working on right now with students. So our first one, the first graph, the first networks that I'd like to talk about are contact networks and degree. And so I'll start with talking about measles and work that I did with my master's student, Christopher Sue, back in 2019, before contact networks were cool. So in the measles contact network, vertices represent people. And for measles, 2 people are connected if they ever breathe the same air within 2 hours of each other. So, so this contact network is very thick. So you can imagine how many people you share air with in any given 2 hours in the day. And so in this contact network, we were trying to understand if we could verify the herd immunity threshold of the CDC and the WHO for measles. And so for that network, we worked with a collaborator, Sune Lehman, who had a network of 700 freshmen at the Technical University in Denmark, Copenhagen. And so for his study, so for the data we were working with, vertices represented students, and 2 students were connected if they ever came within Bluetooth proximity of each other. So that's about 2 meters. And so we thought that's a pretty good estimation of contact. So it's kind of actually a very conservative estimation for contact for measles. And so what we did with this network is we continually infected it with measles and watched measles spread through the population with varying degrees of vaccination. So we would vary some of the vertices, we would vaccinate some of the vertices, and we found in the end, we concluded that the CDC and the WHO's estimates for herd immunity were actually below what we found. We found we needed higher than 95%. From the contact network perspective to guarantee herd, not guarantee, to have a high probability of immunity in our network. And so that was our work that we did with measles before COVID came along. When COVID came along, I had a student, Ryan Solorzano, who was also interested in looking at contact networks. For COVID, the contact networks are a little bit more restrictive than for measles. So for COVID, 2 people are connected if they are ever within 6 feet of each other, or at least for at least 15 minutes. And the CDC just changed this. It used to be 15 consecutive minutes. Now it's 15 minutes over any 24-hour period. And so what Ryan Solorzano wanted to study was in the absence of a vaccine, because we started this work while there was still no vaccine available, in the absence of a vaccine, could we use simply testing and quarantining strategies to prevent the spread of COVID? And so what we were trying to do is we said, okay, well, we'll say we have a certain amount of tests. We'll say they're limited. And if we have a certain amount of tests, who in the network should we test to make sure that if we test and quarantine that person, that'll have the best impact on the overall network? And so, so we tried a lot of different strategies to find in different networks who to test. And it turns out that it was very simple. And the measure that worked the best to determine which people to vaccinate was simply the degree. And so the degree of a vertex is the number of vertices that are adjacent to that vertex. So like A in this example would have degree 3, B would have degree 1. And it turned out that when we were infecting different networks and trying to see if this testing and quarantining strategy would be enough to prevent the spread of COVID, that simply testing the people of highest degree worked best. And so here are just some quick graphs of, we had a high school data set where vertices represented 320 students at a high school, and the students wore sensors on their wrist. Again, it was Bluetooth proximity. And we did all sorts of sophisticated ways to choose the people who we should test and vaccinate. And in all of our tests, just choosing the vertices of highest degree performed very, very well. We found the same thing in preschool simulations. So a similar network, vertices represent preschool students, and 2 preschool students were connected if they ever came within Bluetooth proximity of each other. And again, we found that the testing and quarantining strategy worked best if we chose to focus our tests on those vertices of highest degree, those people with the most contacts. Okay, so that's contact networks. Next is a much more fun kind of network. This network involves rhesus macaques. There are, in our data set for this particular project, there are 159 rhesus macaques on the Cayo Santiago Island in Puerto Rico. And there are 2 types of graphs with these monkeys. One is a grooming network. So vertices represent the monkeys, and 2 monkeys are connected if they ever groom each other. And then there's another network where vertices represent monkeys, and 2 monkeys are connected if they ever sit within 2 meters of each other. So that's kind of that proximity. It's similar to the proximity and contact networks that we were talking about with COVID. Now, in this network, I'm working with 4 of my senior level students, Sho, Iris, Kwa, and James. And what we're trying to understand is how quickly messages can travel in this network of monkeys. And so we're interested in, if monkey A has some information, how long will it take to get to all of the other monkeys? Now, this is particularly important for this group of monkeys because we have data on what the network for these monkeys look like prior to 2018. And then in 2018, there was a very large hurricane that actually ended up separating this island into 2 distinct islands. And so we have these monkeys in the north, and the monkeys in the north got separated from the monkeys in the south, and the ones in the north, their portion of the island wasn't too deforested, but the monkeys in the south, their island was extremely deforested. And so, so the monkeys in the south, it had a lot of trouble obtaining shade. And so on this island in Puerto Rico, it gets very, very hot. And so shade is really important for survival of monkeys. And so we're studying how quickly messages travel between monkeys so that we can see, did the network change? And we have found some preliminary work that the average path length did in fact get shorter. And so monkeys were more social, you could think, after the hurricane, likely, or we hypothesize with respect to that being more social and being able to get more information about like what shade trees, since there are so few, are available, is probably vital to survival. I'm running out of time, but I just kind of wanted to give a good overview of some of the things that I'm working on. I just recently started on a breast cancer social network study with Marilyn Tseng. She's a professor in our kinesiology department. And in this network, vertices represent women in Santa Maria, California, who immigrated from Mexico and their friends. 2 people in this network are connected if they have discussed something important in the last 12 months. So this really is A social network. Okay. And so the thing we're trying to study is women who live in ethnic enclaves, so places where culture is highly preserved, seem to have a much lower prevalence of breast cancer than people who have been living in America for generations. And so we're trying to understand the social network impact of people living in enclaves to see how that is, if that's something that's contributing to their greater health with respect to breast cancer. All right, I will stop now. I really enjoyed hearing the first two presentations, and I really look forward to talking to anybody who wants to collaborate on anything having to do with graphs. Thank you.
Thank you, Theresa. Very, very interesting talk on your multiple projects. And I now open it up to the audience, and that also includes the speakers. Anybody can ask questions, and I see a couple. Let's start off with Ronald, then Michael.
I loved all the talks. Always interesting to hear very different things. Theresa, your talk just grabbed me on something. What are the issues that we as a faculty face here at Sac State, and I'm sure the rest of you do, is communication amongst the people on campus. And there is some sort of philosophy that if you send a message down the hierarchy, you know, to the deans and then the chairs and so on, that somehow the students will learn this. And I'm very convinced that it's about the worst possible method. And I wonder, do you know anything about messages never get to students in a time when they need to hear them? What's a little different than your work is there would be, rather than just having a vertex, an edge hit a vertex, there is the issue of whether the vertex receives, like opens the email or cares about it. Do you have any thoughts on this?
Ronald, that is such a good question. And I thought you were going to travel in a different direction, but the way that you, so I want to talk about the way that the question that you asked, and then something very, very related, which is really very impactful to all of us here is, so Ronald, there's graph measures called betweenness centrality. And so betweenness centrality is this idea that there are these vertices and networks that most of the paths travel through. And so, if you, let's see, if you think there's a fun study, you might want to look it up, about Paul Revere. Paul Revere had very high betweenness centrality. If you look at some of the networks that people could grab from revolutionary times, because so many messages traveled through him. And some people have heard that Kevin Bacon is the center of Hollywood, right? Because most paths travel through Kevin Bacon. And so there are these keystone individuals in almost every network that you see, and they are the ones who can get the message out. And so you might be able to identify some keystone, you know, if you look at these communication networks, you might be able to identify some keystone individuals. And if you get a message to them, it will get out there. Where I thought you were going to go with this was collaboration and communication among faculty. And I have a really good project going on right now with 4 other faculty members and something like 12 students, where we're trying to understand what we're doing right here, which is, I didn't get a chance to talk about it, but the collaboration network of the CSU and UC systems. And so we're looking at who collaborates with whom, and we're trying to find the keystone individuals there, thinking that when you bring in new faculty, you want to connect them to these very, you know, connective people, these people with high betweenness centrality, and hopefully that'll help promote success in their early careers. And so, so for getting messages out to students and helping, you know, researchers to collaborate, both of those are kind of answered by the same measure.
Thank you very much. I'm going to dig into this. Thank you.
Yeah, great. Thanks, Ronald.
Michael.
Yes, I was only able to attend the last presentation, and so my question is about that. So when you model these contacts, say with measles or COVID or any other thing, you model it with a static model. The graphs, once you've defined the graph, it's static. But the situation you're encountering is inherently dynamic, somebody who has not spent time with someone for 15 minutes will spend time maybe, in the next hour with them. So how do you account for that?
Michael, our data sets are so rich, it's already accounted for. Our graphs that we're discussing are temporal. And so we have 5-minute timestamps for the Copenhagen network that we studied measles with. We had 21 days, every 5 minutes, we got contacts. And so we could make sure to say, if person A had measles at timestamp 4, or at timestamp 7, but they came in contact with B in timestamp 2, then of course B could not have gotten measles from A. And so we already have that. So these data sets are extremely rich and they actually are temporal.
Wow.
Yeah, I know. It's incredible.
That's pretty cool.
Yeah.
Thanks.
Thank you.
So, Laurie, I have a question. What constitutes a severe storm? I was looking at your graphs, and there was a lot of yellow there. So, can you kind of frame that so us people like me who don't understand, the variations in storm, can you kind of give us some context to that?
Sure. So the figure that I was showing is put out by NOAA, and they look at billion-dollar impacts. So any kind of natural disaster that had a billion-dollar impact, whether that's due to flooding, for insurance, or say big rains that lead to flooding, or wind, kind of all kind of tied to storm. So thinking about, a hurricane has elements of all of those oftentimes, right? So if it resulted in what was quantified as at least $1 billion of damages and loss, then that event would have appeared on the graph that I had shown.
Great, thank you.
Mm-hmm.
And Theresa, I have a question. We used to do some work in chemometrics, artificial neural networks, and response surface methodology in optimization of our experimentation. I'm an analytical chemist, so we did quite a bit with some colleagues in our microfluidics work, and we found it worked quite well in optimization of experimental parameters. And one could imagine a lot of different parameters in our work. We weren't just focused on 2 or 3. There could be a variety of different variables. So you gave the example of the infections, and I was thinking, how does one parameterize? How does one actually determine how many variables one chooses and which are the most important, and the interplay between those variables? And kind of a follow-up to that, you mentioned the 6 degrees of Kevin Bacon, and how one can relate that to who are the key principles on a campus, kind of following up on Ronald's question. In my work at the Chancellor's office, I'm always interested in finding those key people on campuses who are the kind of the movers and shakers, okay? And so, but there's the pros and the cons. There's those that you want to engage with, and then there are those that you don't want to engage with. So how can one identify the flip side of the coin, those that bring value added to the table, and those that you want to avoid, who you don't want to collaborate with because they don't bring anything value added? So I know there's a lot to bite on there, but it would be interesting to be able to identify, aside from looking through ResearchGate and Google Scholar and looking at how many proposals they submitted, how many are funded, to actually pinpoint, those needles in haystacks. We have 26,000 faculty, 11,000 faculty that are tenure track, and 15,000 that are contingent. It's hard to sort through the muddy waters to find, those diamonds in the rough.
Well, Frank, that's such an interesting question about, is like high degree something that is valuable or not valuable. Like you said, they're the big people. But what we kind of propose and what we think about is that collaboration in general is a choice, right? And so when you choose to write a paper with someone, there is some level of choice, right? Or you're choosing to submit a grant with someone. There's some level of choice. And so we feel that when we find these vertices of high degree, then that means that a lot of people have actually chosen to work with them, right? And so this isn't the same as like maybe someone has a huge citation count and they are, they do work that gets published a lot, but they're not very fun to work with. Those people wouldn't get high betweenness in a collaboration network. And so I feel like since we don't care so much about like, the actual citation count or the impact factor of the individuals, that we really are just interested in the collaboration. We feel that I would be happy to work with anybody who has high betweenness centrality in a collaboration network, because that tells me that they know how to work with other people. And you don't get the people who might not be excellent to work with. Does that seem?
Yeah, that's why I try to stress in people I choose, do they have that right temperament?
Yes, yes. And you suppose someone, if everybody wants to collaborate with them, likely they do, right? They're people who like to work with other people, who are fun people to work with.
Yeah. I mean, it's not only what they bring to the table, but if this proposal is funded, it's like a marriage.
Yeah.
You may be involved with these people for 3 to 5 years, so
Yes.
you better be happy in this marriage, because writing the proposal is work, but it's easier than working with somebody for 3 to 5 years, and you want to make sure that 3 to 5 years is going to be
Pleasant.
a good engage. Yes, very pleasant.
Yes, I agree. Thank you.
Thank you. Questions from the speakers, or from people here on the Zoom? Ronald.
If someone else has one, but if not, I'll sneak one in. It's always funny to have to go through one of these mechanisms to speak to someone on our own campus. But Lauren, I have some data that maybe we might be interested in together on depths of tropical rivers that I've worked on for many years. And I have data loggers that collect these. It looks like something going up and down and up and up and down. And I'm interested in extracting information about storm events, much related to some of the things that Lauren was talking about. So it's time series, complex time series data. Is that something that might pique your interest at all?
Yeah, absolutely. And I can certainly take a look at it and kind of, dig into the data a little more and see what we're thinking.
Okay.
Yeah, I'd be happy to talk to you about that.
Perfect. And it's not perfect data like all of our data.
It's
messy. There's missing bits, all sorts of stuff. Okay, good. I will do that. Thank you.
Yeah, of course.
Thank you for the comment, Anya. Okay. Well, I certainly would like to thank our speakers today. It's been very interesting to hear a lot about what you're doing in terms of your research, and if people want to contact any of our speakers, feel free to contact them. Perhaps it could lead to a collaboration. Certainly, that's something we've been talking about here in the Q&A, and perhaps lead to a proposal going forward. We have coming up on November 30th at 10 a.m. Advances in the Social Behavior and Economic Sciences. We also have a program officer from NSF speaking. This will highlight some of our exemplars that have been funded through the SBE Directorate at NSF. We then come back after our long break, not for me, but for many of you faculty. Friday, January 27th, we have NSF-supported computer and data science research in the CSU. We will have a number of CSU faculty funded by NSF. And then we return again on Friday, February 10th at 11 a.m. for our next virtual research cafe. So we'll continue on with that. So I'd like to thank everyone for attending. Looking forward to seeing you in the future at another STEMnet event. And I hope to see all of you sometime around when I visit your campuses. So take care, enjoy the rest of your week, and have a good one. Goodbye.